Hello, everyone. I'm De Teng from Stony Brook University. Thank you for coming to my presentation, and I will introduce Glint, a GPU-based real-time contact tracing system today. Contact tracing is an essential tool to control the spread of infectious diseases like COVID-19. The potentially infected pupil can be identified if we know the traces of all the pupils. And the number of pupils in an enclosed region could be millions, even tens of millions. To achieve accurate retrieval of human traces, the locations should be sampled frequently. As a result, if raw traces are stored, the space needed could be enormous. Actually, the real-time location data can be processed on the fly to apply some constraints to shrink the size of the data need to be stored. One constraint, the special constraint, is that infections taking effect only when two pupils are within a specific distance. Another constraint, the temporal constraint, is that infections taking effect only after two people keep contacting for a minimum period. And after processing data with a special and the temporal constraint, the total amount of data need to be stored can be significantly reduced. So we define valid contact as two pupils stay within the maximum distance for a minimum period. And it raises a challenge to retrieve the valid contacts for few spatial and temporal constraints from large-scale constantly updated location data in real time. That is why we propose Glint, a GPU-based real-time contact tracing system. The input of Glint is a real-time locations of a set of pupils, and the output will be the valid contacts. Let me first introduce some features of GPU processing briefly. Each GPU is composed of multiple streaming multiprocessors, and each streaming multiprocessor contains multiple cores. And all threads executed on the same streaming multiprocessor execute the same instruction at the same GPU cycle. So conditional statements are inefficient on GPU. On the other hand, dynamic memory allocation is expensive on GPU. So all the required memory space should be pre-allocated before the execution is started. Here is our view of the Glint system. The sampled data will be spatially and temporally evaluated before being persisted. To fulfill the spatial constraint, we need to conduct a within-range query over all the sampled locations in real time. First, we need to index the moving objects considering some features of the distribution of real-world human beings. First, in most cases, the population is not evenly distributed. As objects are not evenly distributed, tree-structured indexes like R-tree and quadtree need to be facilitated to index special objects. And quadtree is chosen in Glint to index the moving object as it is simple and fit GPU processing very well. A typical bottom-up method used to index objects with quadtree on GPU can be implemented in two steps. First, we can generate a partitioning schema level by level in a bottom-up manner. Second, we can index all the points according to the partitioning schema just generated. One obvious disadvantage of this method is that it needs additional efforts to generate the partitioning schema. Luckily, the population distribution does not change significantly in a short period of time. Therefore, it is possible that we can index the latest locations of a pupil with a partitioning schema built with their previous locations. However, the population distribution changes when time stretches longer. As people move time to time, if we continue using the same partitioning schema for all rounds of locations, some nodes will be underflowed, where some nodes will be overflowed. We take three approaches to handle this issue. First, we set the capacity of each partition buffer slightly bigger than the leaf node size. And second, we use a globally shared overflow buffer to hold the overflowed objects. And third, we dynamically update the partitioning schema at the leaf node level. We split the overflowed nodes and merge the underflowed nodes. Next, we show how the within query can be conducted for all the objects with this index. For each point P, a within query needs to be conducted with the index in three steps. First, a range query is conducted over the partitioning schema to retrieve the partitions that are within the contact distance from P. And second, we push P into the buffer of the partition that contains it. And third, after all the points are assigned to a proper partition, we calculate the distances between P and the partition points in the candidate partitions and report the ones with the contact distance from point P. However, conducting range query over a tree-based index needs stack-based operations like depth-first search or breadth-first search, which are inefficient on GPU. On the other hand, it is efficient to locate the target partition that contains a specific point using GPU, as the point is contained by exactly one child in each level, thus no stack-based operation or conditional statement is needed. For better efficiency, the range query over the index on GPU for all points can be conducted in 2 steps. In the partitioning step, for all the points, we assign them to the partitions that contain them. And in the filtering step, we conduct a range query only for some of the points who are too close to the boundary or the boundary points. Let's first look at the partitioning step. During the partitioning step, each point is assigned to a specific partition level by level. Meanwhile, during this process, the lowest node in the path of which the distance from the target point to the boundary of the node is larger than the contact distance will be recorded as the filtering root node. Then in the filtering step, the range query can be conducted starting from the filter root instead of the root of the tree, and all the candidate partitions must be covered by the filtering root node. Now let's move to the filtering step. As can be seen in this example, the depth of the filtering root for different boundary points could be very different. As a result, the processes of the range queries conducted for different boundary points could also be very different. This table gives a number of nodes processed for different boundary points. It shows that the number of nodes processed varies a lot among different boundary points, and the load of threads is imbalanced. To solve this problem, we adapted the shared stack method, which is sharing a single stack by all the threads in the same block. Here is an example of a shared stack-based method. Initially, the boundary points and their filtering routes are pushed to the shared stack by all the threads in the same block. Then those entries are processed altogether by all the threads. As a result, the load for all the threads in the same block is almost balanced. And the partitioning and the filtering steps now produce a list of OP pairs where O is a point and the P is a partition that are within the contact distance to O. So geometry computations are needed in the refinement step to truly recognize the points in partition P that are within the contact distance, which leads us to the refinement step. Due to the nature of the data partition index and the reuse of the partitioning schema, the number of points in each partition is different. It varies from 0 to the partition capacity. Actually, the distribution approximately follows the normal distribution. And if each thread processes one point partition pair, then the execution will be bounded by the pair with the maximum number of points in the partition. For example, if we have 3-point partition pairs for evaluation and each of those partitions contains 67, 25, and 37 points respectively, and if each thread processes 1-point partition pair, as all the GPU threads execute the same statement at the same time on the same streaming multiprocessor, all threads need to process 67 point-to-point pairs, and a lot of those evaluations are wasted. To better utilize the GPU, we process each point partition pair with multiple threads, which we call it refinement and rolling. And each thread just processes a fixed number of point-to-point pairs, or the refinement granularity. For the same example given above, if we set the refinement granularity as 10, much less GPU cycles are wasted, and the overall utilization of GPU is increased. Next, the retrieved contacts need to be further evaluated to fulfill the temporal constraints. And in Glint, we use a hash table to maintain the currently contacted objects and evaluate all its entries after every round of processing. The key of the entries in the hash table will be the integer generated by combining 2 object IDs with a control pairing function. And the value will be the information of the contact for example, the start and end time of the contact. Here gives an example of how the context can be temporarily evaluated. The minimum duration for a valid contact is set to 2 seconds. And anytime a contacted pair of objects is identified, an insert or update operation is conducted over the contact hash table. And after each round of processing, all the entries in the hash table will be evaluated. And by checking the end time of the contact, we remove the contact which has ended, but the duration is not long enough. Otherwise, the ended contact whose duration is long enough will be copied into the valid contact list for persistent. And we conducted tests over 10 million traces, which are sampled every second. This figure shows the average latencies for processing one round of locations with either CPU or GPU. It shows that using a typical GPU takes about only 200 milliseconds to retrieve valid contacts from 10 million locations, which is more than 2 orders of magnitude faster than using a single-core CPU, and 5 times faster than using an advanced CPU, which supports up to 48 threads. And 3 parameters can be configured to help Glint achieve optimized performance. And Glint supports different contact tracing scenarios as well. Due to the time limit, they will not be discussed here. Please refer to the paper for more details. In conclude, we adapt the GPU to the contact tracing data processing scenario with multiple novel techniques and achieve tens of millions scale contact tracing data processing in sub-second level. Thank you for all your listening, and it's my pleasure to answer all your questions.